Hello, I'm Lachlan Gibson from the University of Queensland, and I've been working with Jacko and Yoni Nazarathy to develop a novel implementation of Q-learning for the Whittle index. This is essentially a new way to control a system of k restless independent projects where each project exists in some state n, and exactly m projects can be activated at each time step. In this example, the first and third projects are being activated. All projects then transition states and yield rewards with probabilities depending on whether they were activated. All projects can transition, which is why the system is called restless. The controller objective is to maximize the expected time average total reward across all projects, where here R represents the reward given by project K in state N under action A at time T. Pi represents the controller policy, which decides which M projects to activate, given the combined state of the whole system. The size of the combined state space scales exponentially with the number of projects, making them computationally intractable in larger systems. Therefore, it's common to focus on index policies, which compute indices for each project independently, and then activate the M projects with the highest indices. The Whittle index is one such index, which extends the Gibson index to restless systems. Unlike the Gibson index policy, the Whittle index policy is not necessarily optimal, but serves as a good heuristic. However, the Whittle index policy is asymptotically optimal as the number of projects grows for a fixed ratio of m and n. To compute the Whittle index, we consider the related problem of controlling an individual project. In this case, at each time step, the controller must decide whether to activate the project. But activation now involves a wage of lambda. Therefore, the goal is to identify a policy phi, which maximizes the expected time average profit, beta, both of which depend on lambda. Therefore, we get the following dynamic programming equation linking beta to q values, which represent the expected relative time average profit for wage lambda when starting at state n and doing action A. The Whittle index at state n is the wage required to equalize the expected time average profit for both actions at that state. Here we assume the system is indexable, following the law of diminishing marginal returns. That is, increasing the wage will increase the difference in active and passive Q values. Interpreting the Whittle index as the marginal productivity rate, any wage less than the Whittle index results in the active action being optimal, while any wage more than the Whittle index results in the passive action being optimal. If the wage equals the Whittle index, then both actions lead to the same expected time average profit. The Q values of an indexable system form piecewise linear functions of lambda, forming structures similar to this. The corners of these functions occur at the Whittle indices, forming regions of fixed optimal policy. In each region, the optimal policy activates states whose Whittle index is larger than the wage, while not activating those whose Whittle index is lower than the wage. As a corollary, the optimal policy in the far right region, where the wage is larger than all the Whittle indices, is to be passive at every state. This is true for any indexable system. Similarly, on the far left, where the wage is less than all the Whittle indices, the optimal policy is always to activate the projects regardless of the state. Remember that computing the Whittle index looks at the related subproblem of controlling a single project and maximizing profit, while the original problem is to control a system of many restless projects. Q-learning provides a way to simultaneously solve the subproblem while controlling a full system of projects with unknown transition probabilities and expected rewards. The general procedure works as follows. Initial estimates of Q values and Whittle indices are produced, usually as 0 or random values. Then for each time step of control, the controller decides whether or not to explore. If the controller explores, it will randomly choose M projects to activate. Otherwise, the controller activates the M projects with the highest index estimates. This leads to new observed transitions and rewards for all projects, which can be used to update Q values and Whittle index estimates in the subproblem. Under appropriate assumptions, the Q values and index estimates should converge over time, so the controller policy converges to the Whittle index policy. Avrachenkov and Borkar recently published an implementation of this kind of algorithm and proved it did indeed converge under certain assumptions. In their implementation, they maintain estimates of Q values at each Whittle index, indexed by I, as well as the Whittle index values at each time step t. For each observed transition from state n to m under action A with the reward r, typical relative Q updates are computed using equation 7. Alpha represents the learning rate, which can depend on the time step, and Q bar represents the average Q value across all states and actions. The Whittle index estimates are updated via equation 9, which increases the estimate in proportion to the difference in estimated active and passive Q values. Delta is the Whittle index learning rate, and generally should be smaller than alpha. Our novel Q-learning implementation follows a different approach, a kind of policy iteration. Rather than learning Q values at the Whittle indices, our method uses Q-learning to learn the line segments in the regions between the Whittle indices. And unlike Avrachenkov and Borkar's method, which learns the Whittle indices directly, our method estimates the optimal policies between the Whittle indices from which the Whittle indices can be computed. Consider the expected relative profit when following a fixed policy phi. Equation 10 represents a system of dynamic equations that compute these values. Note that by fixing the policy, the summand has dropped the max operator, and the system has become linear. In this way, the Q values can be seen to be linear functions of lambda, where the intercept represents the Q value for zero wage, while the gradient h represents the expected relative average number of times the project should be activated under policy phi. Substituting equation 11 into equation 10 allows the system to be fully decomposed with separate expressions for the intercept and gradient, both of which are now fully independent of lambda, but rely on knowledge of the policy. Implementing the method involves maintaining estimates of Q and H values and optimal policies in each region, indexed by I at each time step t. The Q and H values are updated from the same transition information separately using equations 14 and 15. Notice that these updates do not include any estimate of the Whittle index. Instead, they rely on an estimate of the optimal policy to predict the action of the next step. This provides a strong advantage over Avrachenkov and Borkar's method, especially when computing Q values in the extreme regions, where the optimal policy can be known with certainty or high confidence. To estimate the optimal policies and Whittle indices from the Q and H values, we exploit the structure of indexable systems. I'll demonstrate the procedure with this example. Beginning at the right-hand side, where the optimal policy is known to be completely passive, the marginal productivity rate is maximized by state 2. So the Whittle index of state 2 is estimated to be this rate, and the optimal policy in the next region needs to activate state 2. This process is then repeated in the next region, where of the remaining available states, state 1 maximizes the marginal productivity rate, so the Whittle index of state 1 is estimated to be this value, and the optimal policy of the next region needs to activate state 1. Finally, there is only a single state available, which gives the Whittle index estimate of state 3. Now, this process can also be performed in reverse, starting from the left-hand side, where the optimal policy is known to activate all states. From here, the marginal productivity rate is minimized, providing an estimate of the Whittle index of the third state and indicating that the next optimal policy should not activate the third state. Actually, in practice, we combine these approaches, alternating between the left and right regions until they meet in the middle. Let's look at an example system with 100 projects, where 20 are activated at each time step, For simplicity, we also use a fixed exploration rate of 10%, meaning at each time step, there's a 10% probability the controller will activate projects randomly, and a 90% probability the controller will activate projects with the highest estimated Whittle indices. In this system, every project follows the same transition probabilities and reward structures. Each project exists in one of 5 states. Whenever a project is activated, it is reset back to the first state and yields no reward. Whenever a project is not activated, it has a 90% probability of increasing to the next state, capped at state 5, and a 10% probability of resetting back to the first state. The rewards for passive action are always positive, but diminish with the state number. Intuitively, you might see that the best strategy is to activate projects in the highest states. This thought is consistent with the Whittle index policy, which evaluates the Whittle indices to be strictly increasing with the state number. Here we show both methods correctly learning the Whittle indices. Dashed lines represent the true Whittle index values, while the solid lines represent the estimated values by each method at each time step. On the left, you can see that the estimates in Avrachenkov and Borkhar's method exhibit some oscillation. We believe this is caused by error introduced by incorrect Whittle estimate values in the Q-value updates. Our method is more noisy, which is probably a result of estimating the Whittle indices from the ratio of differences in the Q and H values. Let's consider another example system. Here, the projects represent students, and the controller is a school who needs to assign 10 mentors to 10 students each day. Again, the controller uses a 10% exploration rate. Each student exists in one of 5 study levels. Whenever a student self-studies, they have a 70% chance of decreasing study level and a 30% chance of increasing study level. Whereas if the student is mentored, there's a 30% chance of decreasing study level and a 70% chance of increasing study level. The reward from each student is independent of the action and increases with the study level with diminished returns. In this case, the Whittle index policy prioritizes students in the 4th study level, and then 3rd, 2nd, 1st, and then 5th study level. Note that the 3rd and 4th Whittle indices are very similar, indicating that both are similar priority. This time, the learning rates are fixed, so the Whittle index estimates only converge to within a small balls about the true values. Notice that in this case, our method appears to converge much faster, but is also noisier. Let us compare the performance of the full system. The left figure shows the proportion of 32 simulations that correctly identify the Whittle index policy. You can see that in this example system, our method, shown in orange, learns the Whittle index policy earlier and much more often than Avrachenkov and Borkhar's method, shown in blue. Similarly, the right figure shows our method achieves a lower cumulative regret, where cumulative regret represents the cumulative reward lost by following the prescribed algorithm rather than the true Whittle index policy with 10% exploration. Looking at the average normalized rewards on the left and the cumulative rewards on the right further demonstrates the performance difference in this particular example system and control parameters. More work is required to further explore the differences in methods, as well as optimize our new implementation. Specifically, we wish to improve the stability of our method so that the Whittle index and policy estimates are less noisy. We want to formally prove that the method converges under similar requirements to Avrachenkov and Borkhar's method. We want to compare methods under a broader range of systems. And later, we also want to see if our implementation is compatible with any deep learning methods. Thank you for listening.